All right, so this is going to be our presentation on our dynamics project for MES 208, section 605. We're group 8. My name is Logan.
My name's Connor.
And my name is Caleb.
Let's get into it. So for this project, we're going to be determining the angle at which an M2 Bradley must fire to hit the intended target at a known distance while traveling at a constant velocity towards that target. In this report, we're going to go over some of the assumptions and calculations that we used.
First, going over some of the background information, we have that we're shooting a M791 round out of the M2 Bradley, and that we're trying to hit a target of 5,000 meters away. The constant speed that we chose for the M2 Bradley is 15 meters per second towards the target.
Some of the assumptions that we used. The classification of the ammunition for the projectile due to the shape of the projectile. This is classified as a G7, which has a known drag coefficient of 0.2. We assume that the drag coefficient because it allows for more precise calculations of the projectile trajectory. The initial velocity of the projectile is known at 1345 meters per second. The cross-sectional area of the projectile is known from a formula that we used in one of our references. We converted 1.35 centimeters, which is the diameter, to meters, found the radius, and used our formula to find the area. The mass of the projectile is a known mass that we found in one of our references. The limits of turret angle is also in one of our references, and this limits the angle at which the turret could fire between -9 degrees and 59 degrees. The velocity of the tank, we know the max velocity of the tank, but we chose 15 meters per second towards the target as our assumption. Target distance and height is a set distance. The range of the tank is 17,500 meters, but we chose our target to be sitting at 5,000 meters. Air density is going to be air density at sea level. We're going to be using an XY coordinate system, also known as 2D. This simplifies our problem. The calculations are still intense. We're going to have a constant mass for our projectile, so mass will not change. There will be no crosswinds, so winds will not be changing the direction of our projectile.
So going over the FBDs of our projectile, the topmost FBD is the one showing the bullet just as it exits the barrel of the M2 Bradley. The second or middle one is showing the bullet when it's at max gravitational potential, or its Y, it says max Y position. The third and final FBD is showing the bullet as it's falling from that or accelerating towards the ground. The next part is the visualization of the tanks. So this is to show that the tanks are on a level ground for the X direction. Going into the dynamics concepts, we're going to go over Euler's equations, equations of motion, relative motion, and some of the FBD analysis that we just did. First, so for the relative motion, we have the velocity of the bullet. So we have to take in the velocity of the tank plus the velocity of the bullet with respect to the tank. And that gives us 15 plus 1345. So that comes out to be a total velocity of 1360 meters per second. And then
Next, going into some of the equations of motion. So in the X direction, we have only drag. If you look about right here, you can see drag changes with total velocity. So to split it up into components, you have to multiply by this 1360, but also 1360 cosine of theta. You can't just square the X component. And the same will be for the Y. We used the dynamic concept F equals ma to solve for acceleration. And next, we use Euler's equation to actually solve for velocity and position in each direction. And essentially, the velocity in the x is equal to velocity in the x plus the acceleration in the x times a small change in time, and vice versa for position. We also use linear interpolation to best estimate the point where it hit. Some of the MATLAB code that we used, I'll go over to MATLAB. Um, when you run the code, it's going to output the best angle, which is 52.9 degrees roughly. The projectile actually hits 5,000.2 meters away, which is zero point 0.2 meters away from our intended target. But because it fell within our 1 meter tolerance that we set, we consider it to be a hit. And if we go over here to the figure, this is what is actually, this is the figure created by the code. It's showing we're starting at a distance of 0 and we fire. This is a trajectory and we get to 5,000 meters. Going over some of the code more in depth, we created our initial conditions up here. You can change some of these, so you can actually do this for more than just the M2 Bradley. Then we are going to use the force of drag and stuff. Total velocity is the square root of velocity in the x plus velocity in the y, each of those squared. These are our formulas for acceleration, and this is where Euler's comes into play. Initially, we created a range of 5,000 angles to check through, and then the code essentially is going to check through those 5,000 angles and find which one hits the closest, and then it's going to print that out down here.
In conclusion, this project successfully determined the optimal firing angle for an M2 Bradley to accurately hit a stationary target located at around 5,000 meters away while the vehicle is moving towards the target. The firing angle needed is 52.9 degrees from the horizontal axis.
And because we use Euler's, this is going to be as an estimation. It's not completely exact, but Euler's is the best estimate we can find to show that 52.9 degrees is needed. Thank y'all.